7 of Albert Einstein's theories that changed the world. Prolific thinker and scientist Albert Einstein changed the world through his work. Here we look at 7 of his most significant contributions to our understanding of the world. Albert Einstein is considered to be one of the greatest minds of the 20th century. His contributions to physics, such as the special and general theory of relativity, continue to exert influence today. But his list of achievements extends beyond just relativity and physics. Join us as we take a look back at some of the most significant discoveries and theories put forward by Albert Einstein. 1. Quantum theory of light. Einstein proposed his theory of light, stating that all light is composed of tiny packets of energy called photons. He suggested that these photons were particles, but also exhibited wave-like properties, which was a revolutionary idea at the time. Additionally, he conducted extensive research on the emission of electrons from the surface of metals when they are hit with light or a stream of photons. This laid down the foundation for his future research on the photoelectric effect, which we will discuss later in this article. 2. Special theory of relativity. In Einstein's studies, he began to notice inconsistencies in Newtonian mechanics in their relation to the understanding of electromagnetism, specifically to Maxwell's equations. In a paper published in September 1905, he proposed a new way of thinking about the mechanics of objects approaching the speed of light. This concept became known as Einstein's special theory of relativity, and it changed the understanding of physics at the time. Einstein's revelation was that observers in relative motion experience time differently. He realized that it is possible for two events to happen simultaneously from the perspective of one observer, but occur at different times from the perspective of the other, and both observers would be right. Understanding the special theory of relativity can be a little difficult, but we'll boil it down to a simple situation. He began with the idea that light always travels at a constant speed of 300,000 kilometers per second, and asked what would happen to our ideas of space and time if that were the case. Now imagine that an observer is standing on a railway embankment as a train goes by, and that each end of the train is struck by a bolt of lightning just as the train's midpoint is passing the observer. Because the lightning strikes are the same distance from the observer, their light reaches his eye at the same instant. So the observer would say the two strikes happened simultaneously. However, there is another observer, this on the train, sitting at its exact midpoint. Because the train is moving, the light coming from the lightning in the rear has to travel farther to catch up, so it reaches this observer later than the light coming from the front. This observer would conclude the one in front actually happened first, and both observers would be correct. Einstein determined that moving through space can also be thought of as moving through time. In essence, space and time affect each other, both being relative concepts in relation to the speed of light. Number 3. Brownian motion. For anyone that has made it through a high school chemistry class, Avogadro's number might ring a bell. Although first described by botanist Robert Brown in 1827, Brownian motion wasn't formalized until the 1900s. First by French mathematician Louis Bachelier, and then by Albert Einstein in 1905, before he proposed his theory of relativity. Brownian motion is the erratic movement of particles in a fluid. In his paper, Einstein modeled the motion of pollen particles in water, providing groundbreaking evidence to support the existence of atoms and molecules. Additionally, the paper also described the best way to calculate Avogadro's number, which is the number of entities, atoms, molecules, ions, etc., in 1 mole of a substance. His work laid down the foundation for the experimental work of John Perrin, who carried out experiments using a high-precision microscope to verify Einstein's work. He successfully calculated Avogadro's constant and definitely proved the existence of atoms, for which he received the Nobel Prize in 1926. 4. The Bose-Einstein condensate. In 1924, Einstein was sent a paper by Indian physicist Satyendra Nath Bose. The paper discussed a detailed way to think of photons of light as a gas. Einstein generalized Bose's theory to an ideal gas of identical atoms or molecules for which the number of particles is conserved. Einstein worked with Bose to extend this idea to atoms, which led to a prediction for a new state of matter, the Bose-Einstein condensate. The first example of this state was produced in 1995. He also predicted that at sufficiently low temperatures, the particles would become locked together in the lowest quantum state of the system. This phenomenon is called Bose-Einstein condensation. A Bose-Einstein condensate is essentially a group of atoms that are cooled very close to absolute zero. When they reach that temperature, they hardly move in relation to one another. They begin to clump together and enter into exactly the same energy states. This means that, from a physical point of view, the group of atoms behaves as if they were a single atom. We now know that this only happens for bosons, particles with a total spin that is an integer multiple of h, the Planck constant divided by 2 pi. Number 5. General theory of relativity. In 1916, Einstein published his General Theory of Relativity. This paper generalizes the concepts of special relativity and Newton's law of universal gravitation, describing gravity as a property of space and time. This theory has aided our understanding of how the large-scale structure of the universe is set up. We know that Newton helped quantify gravity between two objects as a tugging of two bodies, independent of how massive each one is or how far apart they are. Einstein determined that the laws of physics hold constant for all non-accelerating observers and that the speed of light is constant no matter how fast the observer travels. He found that space and time were interwoven and that events that occur at one time for one observer could occur at a different time for the next. This led to his theory that massive objects in space could distort spacetime. Einstein's predictions have helped modern physicists study and understand black holes and gravitational lensing, among many other structures in the universe. Number 6. The photoelectric effect. Einstein's theory of the photoelectric effect discusses the emissions of electrons from metal when light shines on it, as we alluded to before. Scientists had observed this phenomenon, but had been unable to reconcile the finding with Maxwell's wave theory of light. His theory of photons aided the understanding of this phenomenon. He theorized that when electromagnetic radiation, light, hits a metal surface, there is an emission of electrons, which he named photoelectrons. This model forms the basis of how solar cells work. Light causes atoms to release electrons, which generate a current, thus creating electricity. Number 7. Wave-particle duality. Albert Einstein's work on the development of the quantum theory was some of the most impactful work he ever accomplished. During his early career, Einstein persisted in asserting that light should be treated as both a wave and a particle. In other words, photons can behave as particles and as waves at the same time. This became known as the wave-particle duality. He is quoted as saying this on the subject: "We are faced with a new kind of difficulty. We have two contradictory pictures of reality. Separately, neither of them fully explains the phenomena of light, but together they do." As we think about all of Einstein's work, we have to also consider how it influenced those who came after him. Einstein's work has influenced modern quantum mechanics, the model of physical time, the understanding of light, solar panels, and even modern chemistry. He relentlessly questioned the world around him. This is what made him great, his infinite curiosity about the world. The important thing is not to stop questioning. Curiosity has its own reason for existing, remarked Einstein. Albert Einstein's accomplishments have unequivocally influenced our understanding of physics as we know it today. Thanks for watching. Like, share, and subscribe my channel. See you in the next video.